Hi, this is the video for section 2.3 of A Student's Guide to the Schrödinger Equation. This one's all about Hermitian operators. If you looked at the last section, you saw that there was quite a bit of discussion about an expression like this, which involves bra phi, then an operator O, and ket psi, in which case phi and psi represent quantum wave functions, and these are both eigenkets of operator O. We said in the last section that if we apply that operator to psi, we know what it yields. It yields a constant times psi, so we write it like that. And lambda being a constant, it means we can either move it out to the right or out to the left, and we show that down here, where lambda has been moved out to the right or out to the left, leaving the inner product of bra phi and ket psi. We're going to do more with that a bit later, but for now we're going to look at this left side. And one way to look at that is that we have the bra phi heading, as it says here, toward an encounter with the result of operating on ket psi with operator O. That's going to take the form of an inner product. But there's another way to look at this, that here's an expression in which the operator is to the right of a bra, and that expression is moving toward an encounter with the ket psi. So the question is, what do we do with this? You can look at that operator as going either way, to the right to operate on the ket, or to the left to operate on the bra. But as it says here, there's a bit of subtlety in how you let this operator operate on that bra. We'll get to that in a minute. But first, consider this. Here we've taken this operator, which is to the left of the ket, and moved it inside the ket symbol. And at first that might look a little strange, but you have to remember that what's inside that ket symbol is just a label. We said that label refers to the vector which this ket represents. So now, instead of just representing psi, this ket represents the vector that comes about when you operate on psi with operator O. We know that forms another ket, and that ket can be written like this. So now we have a new ket, and when we form the inner product with phi, that looks like this. So that's the way to think of it when the operator goes to the right. But to go to the left, one way to go about that is to move the operator inside the bra. Now notice when we do that, something else appears. It's this cross symbol in the exponent of O. This O cross operating on psi is just a label, and that label refers to a vector. That vector is the vector formed by letting this O cross operate on vector psi. The bra, shown by this, is just the dual of that ket. As it says here, that cross represents the adjoint of the operator. And if you want to know how to take that adjoint, that's explained right here. Here's a representation of a 3x3 matrix representing operator O hat. Its adjoint is then this. And notice that two things have happened. One, every row here has become a column in the adjoint. And two, every element has had its complex conjugate taken. So two things happen. Transpose, which means making rows into columns, and complex conjugation. That process is fairly straightforward if you're thinking of a single column vector, like this ket A. If you take the adjoint, you turn this one column into a row, and you take the complex conjugate of every element. That looks like this. But you know what this is? This is the bra. That is the dual of ket A. So when you apply the Hermitian adjoint to a ket, you get the corresponding bra. So that's how O and its adjoint, O cross, differ in form. But what is the difference in their function? Well, here's how I think of it. If O operates on a ket psi to produce a new ket, which we'll call psi prime, then the adjoint of O operates on the bra psi, that is the dual of ket psi, and you get a bra psi prime that is the dual of the ket psi prime. Clean this up a bit. So O operating on psi produces psi prime the ket, and O's adjoint operating on the bra psi produces the bra psi prime that is the dual of ket psi prime. Notice that in writing this, the operators have been outside the ket and the bra. And it is possible to evaluate an expression such as this without moving the operator inside and taking its Hermitian conjugate. How does that work? Well, here's a ket psi, two elements, psi1 and psi2. Here's the corresponding bra, psi1 star and psi2 star, in a row vector. Here's an operator with 4 elements. So another way to look at this without moving the operator inside the bra is to simply write the bra to the left of the operator, just like it is here. So how do you do that kind of multiply? Just like you do matrix multiplication. Multiply these first by the first column, then by the second column, and you get a new row vector. Here's the first element, here's the second element. So we found out how O can operate to the left on a bra without moving inside the bra. But we said on the previous page, we can move the operator inside the bra if we take its adjoint. Let's see how that works. First, we write the adjoint. Remember, it looks just like the operator O, except the columns are now rows and everything has been complex conjugated. So let's write what this is where we've moved it inside the bra. We know that this bra is the adjoint of this ket. We showed that on the previous page. But we can write this adjoint like this, where we've moved this out of the ket, and we know that we can move an operator out of a ket, which we've done here. We still have the adjoint of the whole thing, and now we write out what that adjoint of the operator is. Here's the ket psi, and again, the adjoint applies to the whole thing. So now we do the matrix multiply. This row times this column gives us the first element. This row times this column gives us the second element. And when you take the adjoint of that, you turn this column vector into a row vector, and you take the complex conjugate on psi1 and psi2, takes the complex conjugate off the elements of O, and compare that to this expression. I'll clean that up to make it a little easier to look at. So this is the same as that. In other words, I can operate on the bra with the operator still outside, or I can move the operator inside, take its Hermitian adjoint, and I'll get the same result. That's described down here. Okay, so with some idea of what we can do with operators inside and outside of bras and kets, now we can start to look at an expression like this, in which we move the operator inside the ket, or alternatively, we take its Hermitian adjoint and move it inside the bra. That brings us to a very important type of operator in quantum mechanics called Hermitian. And it's very easy to understand what those are. They are defined by the characteristic that they equal their own adjoints. But how can that be? Pretty straightforward to understand if you look at the matrix representation. So here's operator O, here's its Hermitian adjoint. How can these be equal? Well, first, look at the diagonal elements. Those must equal these. So O11 must equal O11 star. Likewise, O22 must equal O22 star. However many diagonal elements you have, they must all equal their own complex conjugates. And how can that be true? They must be real, because any real number equals its own complex conjugate. All right, another little cleanup. What about the off-diagonal elements? Well, it must be true that O21 is equal to O12 complex conjugate. Likewise, O12 must equal O21 complex conjugate. So for the off-diagonal elements, each one must equal the complex conjugate of the corresponding element on the other side of the diagonal. You can see that here, where O31 equals O13 star and O23 equals O32 star. That's summarized in that paragraph. But why are these of special interest? What's so great about an operator that equals its own Hermitian adjoint? To understand that, let's look again at this expression, in particular, this second equality. Remember, we've moved the operator into the ket and into the bra, taking its adjoint. But if O equals its own adjoint, then I can replace that adjoint with just O. And now compare this to this. Look at what that's telling you. It says that you can operate on the second member of the inner product, or you can operate on the first member of the inner product, and you'll get the same answer. That, turns out, is going to have very important ramifications. Before we talk about some of those, you might want to look at the function version of this. Here we have the inner product between two functions, f of x and g of x. We form the inner product taking the complex conjugate of the first member. Here we're operating with operator O on the g function. But now we're going to move that operator to operate on F star instead of on G. That means we have to take the adjoint. But since this operator equals its own adjoint, this expression must equal this expression. Once again, you can operate on G or you can operate on F star. You will get the same answer. To see why that's important, look at what happens when we write this expression with O operating to the right and to the left when we feed it the same function psi on both sides. If psi is an eigenket of O, we know what happens. You simply get a new ket, which is lambda psi, or if you operate on the bra, you get a new bra, which is lambda psi the bra. So that means we can write this expression like this. Now we have a constant inside the ket or inside the bra. Can we just pull that out? Well, you have to think about that a little bit. First of all, let's worry about the case where it's inside the ket. It says here that a constant inside the ket or outside the ket doesn't matter. You don't have to do anything. You can just pull the constant right out of the ket. Why is that true? Well, to see that, look at what happens if you multiply C by ket A. Here we've written ket A as a 3-element column vector with x, y, z components. We can move that C inside of each of these. We get this. But we know what that is. That's a ket labeled CA. So therefore, C times the ket A gives the same answer as the ket CA. But what if we want to move that constant inside a bra? It says here you have to take the complex conjugate when you do that. And why is that true? Well, once again, start out just by writing C times bra A and write that out, again in the Cartesian coordinates here, as A star x, A star y, A star z. Move that C inside, looks like this, but then write that in a different way. Write C A sub x star as C star A sub x quantity star. Same thing for the y and z components. But look at what that is. That's just 3 elements complex conjugated. So that is a bra that looks like C star A. Why is that a bra C star A? Well, remember, the bra C star A is the dual of ket C star A, in which we write that ket with these 3 elements. So therefore, when you move a constant inside a bra, you have to take the complex conjugate of it. Likewise, if you want to move it from inside to outside, you have to take the complex conjugate. So, knowing what happens to constants inside bras and kets, we can look at this expression a little differently. Here we've got a constant inside a ket. We know we can pull that out, not have to do a thing to it. But this constant inside a bra, if we want to pull it out, we've got to take the complex conjugate. So that says that lambda times the inner product of psi with itself must equal lambda star times the inner product of psi with respect to itself. But how can that be true? It must be true that lambda equals its own complex conjugate. In other words, it must be real. So here's an important characteristic of Hermitian operators. They must have real eigenvalues. And here's another important characteristic which you can get by, once again, letting this operator go inside the ket or taking its Hermitian adjoint and moving it inside the bra, which, since it's Hermitian, just gives us the operator inside the bra. Notice in this case, we're using 2 different functions, phi and psi. Now let's say that phi is an eigenfunction of this operator, and it has an eigenvalue lambda sub phi, and that psi is also an eigenfunction, but it has a different eigenvalue, which we'll call lambda sub psi. Well, we can let the operator operate on psi. That'll just produce its eigenvalue times psi. And we can let it operate on phi, which will produce that eigenvalue times phi. We can pull this one out of the ket. We can pull this one out of the bra, taking its complex conjugate in the process, and we get this expression. But we just said that the eigenvalues of a Hermitian operator must be real. So instead of writing this as the complex conjugate of lambda sub phi, we can just write it as lambda sub phi, and that's what we've done here. So now look at what we've got. We've got this expression where lambda sub psi times that inner product is equal to lambda sub phi of that inner product. Or moving this whole term to this side, you get this. That says that the difference in the two eigenvalues times the inner product of the two functions must be 0. But the only way that can happen is either if these two eigenvalues are the same, which we said they're not. We said if these are two different eigenvalues, so that can't be it. It must be that these two eigenfunctions have 0 inner product. What does it mean to have 0 inner product? It means they're orthogonal. So the eigenfunctions of a Hermitian operator, as long as those two functions have different eigenvalues, they must be orthogonal. But isn't it possible for two eigenfunctions to share the same eigenvalue? Sure, that's what we call the degenerate case. And in general, those eigenfunctions with the same eigenvalue will not be orthogonal. But you can always find from a set of non-orthogonal eigenfunctions an orthogonal set. One way to do that is the Gram-Schmidt procedure, which you can read about on the book's website. And once you've got non-degenerate eigenfunctions, you know that they must be orthogonal. So Hermitian operators are important because they have real eigenvalues, because their eigenfunctions are orthogonal for the non-degenerate case, and one more characteristic, which I just mentioned here, they must form a complete set. That means that any other function in that abstract vector space can be made up from those eigenfunctions just by weighting them properly and making a linear combination. So, some important ideas in this section. First of all, Hermitian operators. They can be applied to either member of an inner product and you'll get the same result. They also must have real eigenvalues, and their non-degenerate eigenfunctions are an orthogonal complete set. Later on, in Chapter 4, when we talk about the operators associated with quantum observables, such as position, momentum, and energy, we're going to find that they're Hermitian. That's because the possible results of measurements are given by the eigenvalues of the operator associated with that observable. And you know that results of measurements must be real, so those operators must be Hermitian. And since they're orthogonal in a complete set, that gives us tremendous flexibility to construct solutions to the Schrödinger equation from these eigenfunctions, and then to use them to determine the probability of different measurement outcomes. So, Hermitian operators, very important quantum mechanics. We're going to see an example of an operator called the projection operator in the next section.